Thanks very much and good afternoon. This presentation is set in such a way, it's like a sort of workshop style. So I'll be sort of provoking you with a lot of questions and, requires you to think something about the things I talk about. This talk covers a lot of grounds. And so in the interest of time, I won't go into the details, but what I'll do is I'll highlight publications that came out from the work that we've done. There's 10 or so publications in full. That's, with the data, with the knowledge base. And also the most important thing is that it pinpoints area of anomaly in all those reports that you could fast track your exploration by just looking at where we think the anomaly is. And so this is all available free online through our website. Before I begin, I got a little teaser for you. Look at this map and sort of ask yourself this question. Do the various data types in this, map complement each other, or are they complementary, sort of information? Here we have catchment chemistry, stream sediment chemistry, we had the boreholes with rock chips, and the water chemistry. I know that you probably, smart people, will have the answer by now. But, I won't sort of, give you the answer because we will come back to this later on. But there's something to think about because this is one of the themes of the presentation itself. For this workshop, there's two major themes. The first theme, is this question. What necessary changes are required, in the geochemical world or in the geochemical exploration sort of, area when we transition from best to critical metal. And we got to remember critical metal, includes base metal as well. So there's a bit of overlap there. And second sort of, theme is a tag on, just to explain, just to highlight that hydrochemistry is a really very formidable, exploration tool. And this is very, sort of useful for undercover exploration itself. To answer these questions, basically, we need to go back to the basic. We need to sort of go back and re-examine what geochemical exploration is. Basically, it's trying to answer the questions of what, why, how, and where. Okay, and lots of these questions will be answered when you do a lot of, do a proper sort of review. But it's a how and where is a question that leads to a deposit itself. Another point that we have to re-examine is what's your role as scientists or geologists, in this exploration, because it's not just getting a spade, go and dig a hole and take some sample and dump it to the lab. It's much more than that, and it requires a lot of thinking. The third thing it says, I will show, reassessment, of geochemical data, and it's really sort of critical part of this talk, where we could redirect the future of critical metal, based on the findings that we have there. And then towards the other half of the talk, I will try and integrate the findings that we have from the assessment of data and from all this that we discussed before by complementing, these findings with packages of data or reports that's available through the Geological Survey. Number one, the first package is the open file, company reports that has been compiled, which we call the Queensland Exploration Geochemistry. The second one is the catchment geochemistry, and the third one is hydrogeochemistry. And finally, as a workshop, I will have some take home for you guys. Hopefully that you could use this take home and apply it in your exploration, something that you could learn and you could apply it directly in exploration itself. Well, what is exploration strategy? Basically, when you look at exploration, there's two areas, the ore body and us. When we talk about us, we're talking about explorers and scientists itself. When you start an exploration project, you have to assume that it's clean slate, that you know nothing about it, and it's only through proper research, proper, project review, you will sort of populate these with whatever knowledge is available through the historical amount of data that will answer the why and what question. However, it does not answer the how and where question, because If you know how to find it and where to find it, you got to deposit. Okay. And there is still leftover things that you have to find as geologists. That leads on to the next part. What's your role? Basically, the literature review, the project review would answer some of these questions, the what and the why, but it leaves the how and the where. What entails in the how and the where? Basically, you got to design a program that's enable you to find out what, the how and where. That's the sample, what sample type do you take, what depth do you take, etc., the sample size. And this becomes important as we progress along this talk. How do you handle your samples when you collect it? And these are decisions you have to make before you send it to the lab, whether you need drying, whether it needs milling, you need sieving, etc. And then the dissolution, because there are so many dissolutions, so many leaching types, whether it's leaching, dissolutions, fusion, etc. You got to make this decision so that your end goal would meet what you aim to plan out to do. And what analytical methods, whether it's unifier assays, etc. So these are decisions, are key decisions that as scientists you have to make to answer the why and where questions. It looks simple, but in the early 2000s, I've done a permutations by combining all these different parameters that I mentioned on top there, and it comes up to 2,332 variables. In other words, it's not as simple as it is. And this requires preconceived idea, preconceived knowledge, leading towards a workable and successful outcome itself. Next, we look at the life of a geochemical sample. They have life like you and I too, but unfortunately, their life is pretty miserable. Basically, what's a geochemical sample? It's a sample that you take to try and represent source area. It could be a mountain, it could be an ore body, it could be an outcrop, it could be a sort of salt profile, whatever it is. You're talking about gigatons here. And for us as scientists, we are only interested, we can't take the whole gigaton and analyze it. We could only take one representative sample. And generally, this goes from about 1 kilogram to about 50 kilograms. And if you're doing bulk sample, it goes up to tons. But this is a kind of sort of workable size that you can bring back to the lab. I'll start with an example of 15 kilograms. From that 15 kilograms, you probably, clean it up, spoil away all those weathered areas, and you can get probably 5 to 10 kilograms and crush it. From the 5 to 10 kilograms, you mill only half a kilogram in most cases. And from the half a kilogram, you take only 0.1 gram to go into the lab, or 0.3. That's, if you're really generous and willing to pay the extra money. What's 0.1 kilogram? I took this packet of sugar from my motel. This is 4 grams. 0.1 kilograms means that this packet of sugars can be analyzed 40 times. That's how much sample that goes into a lab, and it means that every sample that you put in is a few grams of, sugar crystals here. So the lab, the machines, the digestions, the analysis will give you numbers. It doesn't matter what quality of samples, how representative, it still gives you a number. It generates good numbers. But the question as scientists, you have to ask yourself throughout this process, is your 0.1 gram representative of the whole big mountains or the gigatons? Does your 5 centimeter core represent the megatons of ore body? If the answer is yes, well done. Move on to the next step. If the answer is no or unsure, tough luck, mate. You have to go through the whole process all over again to ensure that that single 0.1 gram or that numbers that you get out of the machine represents what you are out to achieve. And that is what geochemical exploration is. Next, we look at the exploration conundrum. Well, for anyone who is interested in mineral economics, I think you have to read the report by Simon Markle from GDK. He produced a 2,000-page report about the future of minerals in the world. And from the 2,000 pages or so, it's a very grim picture, because basically it's telling us that we haven't got enough of everything. Say in copper, we are only halfway through what we need. In terms of lithium, we are 10% of that, etc. And we have a 2020 net zero target. Can we achieve that? If we can't produce enough, it means that that's one obvious thing is we got to find more. Yes, we got to find more. But the fact is that there is a discovery drought as well. That's, well, since, the signing of the COP21, that's the Paris Accord, which is signed in 2016. Yes, we do say that, that's $1 trillion worth of, rare earth in the Nordic states or in Malaysia, etc. But these are postulated, sort of, reserved, and they are not a mine or deposit. It takes decades to develop it. Are we really being realistic? Can we really, sort of find it in the mid of 2020? Why can't we find more? Is it because we passed the mineral peak already? Or is maybe we are not successful in finding, more? Well, are we tracking along a tracks that's a well-worn tracks that people have used, and we just track along the same path without looking ahead, whether there's some problems or something blocked in front, and we just follow a recipe book to try and sort of find the next deposit? Or do we really need to change to transition from base metal into a critical metal sort of exploration, area? This is a question we have to ask, and it's a serious question at this point, at this juncture of exploration that we have to ask ourselves. To answer that question, we look at how elements behave. Well, basically, the 103 elements are grouped into 10 different groups. The grouping is because they have shared very similar physiochemical sort of properties. The biggest group, and this is where most critical metals are in the metal transitional or the sort of, poor metal group. They have very similar properties, and people are talking about splitting the transitional elements into two groups further, because the oxygen-loving oxyphilic group towards your right, and the sulfur-loving ones towards your left, sorry. Whichever. Yeah, and the sulfur ones, the chalcophilic ones, behave quite differently. Well, if you look at the traditional exploration, most elements, most successful sort of, mines and, were created when we mine very similar commodities. That's the metal group. There are 15 or so elements covering, the core metals to the metals itself. When we throw in the critical metal, and Queensland is very generous, we got 52 critical metals here, or critical elements here. That's not including lead, silver, gold. If we add that, it would be more. What it shows is this: with this new trend towards critical metal, we are adding not just metal, but we're adding additional groups: the alkali metal, the alkali earth metals, the metalloids, the rare earth, and non-metal itself. So if we compare, between what's traditionally mined and explored and mined and what we have as our target, our new target covers almost half of the periodic table. And what's important is this: the chemistry no longer fits into the metal or the metalloids in a sort of group. It spans across a much wider multiple groups. And therefore, this is a conundrum that you can't use a recipe book exploration method that you find in a lot of manuals and apply it blindly to try and look for critical metal. It really needs a rethink. This table looks simple and boring, but I can assure you it takes a lot of my time, because what I've done is I look at every element, look at the partition coefficients of elements from gems, and then look at what minerals it forms, and then associated minerals, basically into two groups. One, the rock forming groups, and the other one is the mineral groups itself. And anything in between, I'll sort of lump it into a sort of, that either rock or mineral forming groups. What it shows is the critical metals spans across all groups. And it means that there is a strong mineralogic and petrogenetic control on the distribution of critical metal itself. Next, we look at the work done by my friend Bowles Campbell, Ken Collison, and Alan Gregg, looking at sediments, how elements behave in sediments itself. What they've done, this is looking at just Queensland catchment. the sediments in catchment itself, they are strongly biased towards the different clastics as well, into clay or the weathered materials, into rock forming, into anthropologic sort of things that's from mining, etc. In other words, when you look at both of these periodic tables, you know that the sort of normal natural distribution of elements is very much biased towards different rock types, different host types, different grain size. That's really important because it forms in different, it's partitioned into different grouping itself. Now, the next thing is this: we need to readdress geochemical exploration. Well, I asked this question the third time. Is the current exploration methodology still applicable? Well, to answer that, what I've done is this: I've looked at a couple of data sets. One, the data sets that I look at is the Cape York catchment sediment sort of data sets, where I look at the distributions of elements according to different grain size and particle size itself. Related to that point, if it is partitioned differently into different grain size, your sampling technique has to change too, because sampling techniques depends on grain size. The third thing that you have to think about is this effect of nugget effect. Previously, when you talk about nugget effect, everyone talks about gold, silver, rhenium, moly, etc., because these are known things. But from the data processing, we find that nugget effect occurs in critical metal, in non-sulfidic or non-metallic ones too. So it is a really important aspect that you have to think about when you sort of sample critical metal. And probably one of the really critical sort of elements is the analytical methods. And I'll spend the probably a quarter of my time, looking at the different analytical methods itself, which I'll go through. Like I said, we use the overbank, sort of deposits, in this Cape York, Ravenswood, and Georgetown area as training sets. And these are sample sets collected by GSQ, and I've created a lab to process this data, dry, sieve, mill it, and pulverize it before we send to our other collaborators. That's University of Queensland under Professor Massimo Gasparon and Mariki Mosset. And so we work really closely to go through every sort of stage of this. The good thing about this sample, the other thing about this sample is this: at every sample points, we take two samples. One, the top outlet sediment or toss, from top 20 centimeter, and the second one, the bottom outlet sediments or bores from 75 to 90 centimeter. Each of these samples has been sieved to two size fraction, the minus 75 microns and between the 75 and the 2 millimeter size. In other words, every one sample size produces 4 results, and that's a really sort of useful data sets where we train all this understanding with. What I've done is this: I've normalized the cost fraction of the chemistry to the final grain. Okay, what it produced is things like this. I'll just go through briefly on this first graph, what it means. On your y-axis, these are the ratio of the cost fraction divided by the final fractions. The unity line, or the one line, is where you had equal amount of sort of chemistry distributed in the cost of fraction and the final fraction. And anything above that means that it's concentrated in the cost of fraction. Anything below that is concentrated in the final fraction. If you look at the major rock-forming minerals, you find that majority of them falls, or the elements are distributed in the final fraction. This means that the final fraction is very applicable for this sort of study. There is only one exception: sodium, and we've ruled that the reason for high sodium is because a lot of the soils that we collected are saline, and so it gives it higher sort of value for sodium. But otherwise, it's mainly concentrated in the final fraction. We look at these traditional sort of minerals that's been mined, and as expected, the silver and the gold has this nugget effect, whereas the other base metals generally falls within the sort of final fraction itself. Here, I've got rid of a lot of these, sort of outliers, and most of these outliers occurs within the cost of fraction itself. The whiskers just means the distribution itself. And so, in other words, why previous expression method is successful is because the same recipe book applies, to them. It's preferentially concentrated in the final fraction, the minus 80 measure itself. Now, come to critical metal. For rare earth metals, you still find that the recipe book, sort of expression is applicable. Scandium, uranium, etc. is still applicable. But then you come across this group of oxyphilic minerals, which Massimo and I have spent lots of time trying to go through them. We find that there is a lot of residue, undissolved ones, because we use digestion methods to clarify in the causal fraction, because we could see that, there's residue left. In other words, they are underreported. But then just looking at that, you find that the mean, that's tends to be higher. Tin is an exception because tin, it's so hard to dissolve that we always find, that's maximum, sort of amount of residue is in tin. Well, when we sum this up as a table, this is what it looks like. What I have here is, it's the ratio for the Bose and the toss. And on top just shows the different elements. The elements highlighted in yellow are ones that has preferential concentration in the causal fraction. Whereas the one with yellow, that's above the one, or the parity, is ones that has nugget effect, but, it's in one or the other. This is from an unbiased, just total sort of amount of, data that we have, the 502 samples that we look at. If we get rid of the nugget effect and just look at, a more sort of realistic ones without the nugget effect, we had 16 elements still preferentially concentrated in the causal fraction. How does this translate back to exploration? Well, we saw this before, and we plot those 16 elements on this graph and find that now it expanded beyond just metals. For this group, the precious metal, we know there's the nugget effect all along, and this, the oxyphilic ones, we know it's hard to digest. But and these are refractory and hard minerals as well. But what's important is to realize that it expands across the periodic table. This is a table that you've seen before, and when we plot that onto there and plus the ones with nugget effect, we find that about half of these elements occurs within the causal fractions in rock-forming minerals. This has significant implication. It means that when we explore for critical metals, we can't just blindly take one sample, minus 80 image, and analyze for everything, and then expect the results to come true, because you will miss a lot of this critical metal if we use that method itself. Well, knowing that critical metals has a preferential into different sort of samples, or sample size or sample grain, the sampling has to sort of match that as well. This is a classic, sort of, table that's used for sampling based on different grain size. What this shows is that if you had expected causal material, you have to get more samples. And because we don't know, when we talk about causal, we don't know how causal it is. It's really important that you do an orientation study. This is from my experiences. When we were looking for epithermal, sort of gold in the past, the minus 80 image give me very low grade. But when I take the sort of gravel size, that's where all these sort of hidden treasures are. Similarly, unless you do the orientation study, you won't know. And so that orientation study is important when you hit this size fractionation itself. And the other thing, because of nugget effect, it's really important that you take sample duplicates. Normally, you take 1 in every 50. Probably for critical metals, you have to reduce that ratio to 1 to 20 or 1 to 10 even. It depends on, how precise you want it to be. But that's a requirement if you want to get a good results for critical metal, sort of expression itself. This applies also to hard rock, where, especially, for example, if you're looking at rare earth in sort of plutonic rocks, it depends on grain size distribution as well. And this is a classical sampling versus weight, sort of graph that is shown here, that when the coarser it is, you get more samples. Therefore, it's two things that we have come across so far, that you have to change, in terms of, recognizing where critical metals occurs in, its samples. And secondly, the sample size has to increase corresponding, to where the distribution of critical metal is. The second aspect of this is to look at analytical methods. Okay. No matter how good your sample is, if you use the wrong analytical methods, you're probably just as bad as you start without good samples. So what I've done here is I've picked 153 geochemical samples that's done by multiple methods. It's the same sample done by multiple methods. You got two groups of methods here. One is a digestion using 3-acid digest, 4-acid digest, and the aquaregia. And the second group, it's the fusion method by peroxide, by borate, and by fire assay. What we do is what I've done is I look at the higher value in that sample to assume that that's more complete digestions. And so I normalize, yes, divide for every sample the chemistry, of that to the highest value. And peroxides and borate, fusion ones generally have a much higher value. What they produce is this arrays of elements that we have. Again, this is very similar to the last graph, where the one is where it's a parity, where the amount of distribution in the 4 acids and the peroxide is the same. Above the one is that this means that there's higher dissolution in the sample using the method that we test. In this case, 4 acids, 3 acids, or the aquaregia, compared to the peroxide fusion. Below, it means that it's more, dissolution, than the peroxide fusion itself. What this shows is really clear that 4-acid digest and the 3-acid digest matches closest to the peroxide value. In other words, it gives the best results. For the aquaregia, it's fall far below the parity line, except for some of these, traditional ore material, that, copper, lead, zinc fits pretty well with it. I'll do the same thing with the borate fusion itself. And again, this is just comparing 4 acids and the aquaregia. The 4 acids are much better. It fits better. So we know 4 acids is closest to the, to reality. And what I did is I normalized the 4 acids results against the top part is the peroxide and the bottom is the borate itself. Those below that, parity lines shows that this is incomplete digestions. And there are about 15 to 17 elements in both the borate and the peroxide that's incompletely digested using, digestion methods. And this looks a bit deceiving because I should have put the same this is a log scale, and this is 0.6 and this is 0.4. But if you squash the bottom ones, up, you find that they are very similar, except for silver in this case. And there's an explanation for that. It's because silver probably drops out when you use, 4-acid digest due to the chloride, the Cl concentration. In other words, no matter how good you think the 4-acid digest is, there are 15 to 17 elements that's not completely digested. So to be frank, they are not the best. It is not the best. The next 4 slides just sums up the 4 methods, the 4 acids, the aquaregia, the borate, and the peroxide fusions. And these are notes which you could carry with you and decide which elements and what methods you could use. What I've shown here is that those in greens are elements that, these 4 acids can digest. The lighter greens are ones that's better, and the darker greens are ones that's not good at all. And the reds are ones that they can't analyze. For example, the 4-acid digest, at best, it is a near complete digestion. It's not the total digestion itself. And it cannot, dissolve refractory, minerals and oxides, things like tin, tungsten, tantalum, titanium, zircons, etc. It is also not suitable for volatile elements, like arsenic, boron, etc. And so it has limitations on its own. And it doesn't say gold, silver, the fluorine, etc. in that group, in the volatile group as well. Next, we look at for the aqua regia. The aqua regia can effectively analyze up to 65 elements. However, we got to remember it's not a complete digestion. It cannot dissolve oxides and silicates, which are the main component in rock itself. What it's good for? It's good for gold, silver, the precious metal, sulfides, carbonates, phosphates, selenites, etc. But when you come to things that's embedded or trapped inside silicates or oxides, it's not able to dissolve it. And so it's basically considered as incomplete digestion. It's really good for all material where you want just to know just what's extracted from your ore. The third one is borate fusion. I put the word plus or minus peroxide is because some labs combine the two together. Although it's advertised as peroxide, borate, they do use peroxide as mixing. So when you send for peroxide fusion in analysis, make sure that it's just peroxide or it's borate, because some of them mix them. When we talk about borate, there's two things that we are talking about, two flux that we use. One is lithium metaborate and one is lithium tetraborate. They have different, fusion temperature, goes from about 1,000 to 1,200, degrees Celsius. And these methods are really quite good. The only problem with this method is that the volatile minerals are driven off, volatile elements are driven off. And so and also it does not analyze, the precious metals, gold, platinum, titanium, etc. And so there is limitation of that as well. But generally, it sort of flux and dissolves most elements itself. And the last method is the peroxide fusion. When we talk about peroxide, it's a combination of three sodium minerals: sodium oxide, sodium hydroxide, and sodium carbonate itself. So it's a array of flux that you put in, and it has temperature ranging from 600 to 800 degrees. Be careful, because some labs throw in potassium too, because potassium fuses at a lower temperature. And so be sure that when you talk about peroxide, it's just sodium and not potassium involved. Again, it's very similar to borate, except it has a lower temperature. Therefore, it doesn't sort of drive up the lighter minerals. And it has a limitation that it cannot analyze platinum group and precious metal itself. So these are the four sort of summary of the different analytical methods. But I think, by far, the best, it's probably the four acids and the peroxide fusions. But if you want to do gold, precious metal, you still need the aqua regia. Well, coming back to the sort of, teaser that I've passed, earlier in the day. Well, do the various data types complement each other? The set answer is no, it does not. Well, if there is, you probably have to sort of, ask, at what stage of exploration. We just look at them, separately. The catchment chemistry just samples what's been exposed, to the surface that gets aggregated into the catchment, and it covers up to, anywhere up to 5,000-6,000 square kilometers. Stream sediment chemistry is confined to the catchment or the sub-catchment. It's really sort of narrow. Again, it's based on what is, at surface. Water chemistry has a radius of influence ranging from 3, that's what Cyril reckons, but we reckon it's 5 to 7 kilometers. So it has a sort of, diameter of about, 10 to 15 kilometers at most. Rock chips and drill hole, basically it depends on the alteration halo, because in most rocks, that it's recent or recent mineralization, the halo might be just a couple of meters. And so that depends really on how good your understanding is, because it does not, sort of represent the whole region itself. Therefore, you've got to ask these two questions. Are you trying to sort of look for regional, signatures, or you look at localized signatures? If you look at regional signatures, I think the work that we've done, we have pinpointed a lot of regional targets that you could sort of. but we have not sort of pinpointed sort of individual X marks the spot to drill. Okay. And this raises the question whether we are doing exploration or research, because in exploration, there's two components: accuracy or precision and area coverage. Without area coverage, it's not much point for exploration. Whereas for research, you can look at a 1 by 1 square meters and do a good research and still come out with a conclusion for that little area. And so when we come to this data, what we are providing, or what the reports we come up with, are mainly for exploration, for regional sort of coverage itself. Now, to the next part of this, how do we transition in exploration geochemistry from, the sort of non-methodology to the future? Well, first of all, I've got to sort of, highlight the point that in Queensland itself, we spent, the estimation that I've made, in the early 2000s is that we spent over 200 million analytical costs in exploration, just analytical costs. And a lot of this has been compiled in the Queensland Exploration Geochemistry. So it would be pretty unthinkable to walk away from this database. It's best to integrate this into your exploration sort of program itself. The second aspect is this: the Geological Survey of Queensland and our partners, Geoscience Australia, CSIRO, the various universities have worked together to produce reports. And I'm talking about at least 10 reports and probably another 10, seminars or talks on, the results of this collaboration that pinpoints exactly where you need to look at. And these are knowledge-based, reports that you should sort of leverage before you step into the next step, to find, your way and how. There are 5 areas that we'll talk about. One is exploration methodology, and I've released 2 reports, the Geochemistry Toolkit and the domain map, that you can download, free through the internet. The database, there are various databases, but the one I'm going to emphasize is the Queensland Exploration Database, which we just upgraded, like a month ago and released it. So it's available. It has 6 million data points there. That's available to all of you. The third one, it's a catchment chemistry, and we have done, a lot of work on this catchment chemistry through both Geoscience Australia, through GSQ alone, and also, a combined work between us. The fourth one is the hydrogeochemistry, and these are all the reports that has been released, and there are 3 reports released using this hydrogeochemistry as targeting tool, and hydrogeochemistry using the isotopes. And finally, the geology, the overall geology, where you could, this is an old report, but it's still valid until today. Okay, I'll sort of walk through, individual packaging, sort of give you a bit more explanation before I sum up. But the geochemical toolkit, the sort of, catchphrase that we use, is that it's a handbook of practical guidelines and pictorial illustration for optimizing pre-discovery. That's the important word. That's because it's a for exploration, geochemical exploration in Northwest Queensland. Why Northwest Queensland? Well, because the examples that we use are for Northwest Queensland. And the more important thing is that because the funding that we get is for Northwest Queensland. That's why we got to add the Northwest Queensland into it. But you could use that report for anywhere in Australia. It covers both outcropping and undercover, sort of exploration, and it involves, examples of both conventional and unconventional chemistry. Things like, plant chemistry, soil gas, water, isotopes, you name it. We have sort of look at all of them and it's summarized in that report. So if any one of you are interested in exploration, I think that's something that you could refer to. The second one is the domain map. This is really for Northwest Chemistry. What we've done is this is an isopac map around the prospective Mount Isa region. What myself, Dominic Brown, and Les Culpepper has done is to look at the borehole log and integrate these logs, the factual data, with geophysical interpretations and come up with this domain map. And we will be trying to upgrade this next year. So, but what the domain map does is that it has prescriptive recommendations of different exploration techniques that's suitable for the different depths. So we basically tell you this is a method you use for this step. This is a method that you can use for this step. And it's some tool that you could use before, trying to sort of explore how and, to explore, in that region. The second package is the geochemistry data that we have. Basically, there are three sort of different types. The first type is the Queensland Exploration Geochemistry, which I will delve in slightly more. The second package is data that's compiled from university thesis from JCU and UQ. We have compiled data up to 2015, but because of IP reasons, we can't release it through our website, and it has to be released through respective university. Those data are compiled by us, but you can get those data through the respective university itself. And the third data, it's those data embedded in reports. I've given you the list of reports, and there are more in GSQ that you could use, to sort of find out not just data, but knowledge base as well. Well, what's the Queensland Exploration Geochemistry? It's a database created, through the funding of Amira, given to TerraSearch. And Simon Beams and Dave Jenkins developed this exploratory data management system. This system is about 30 years old. It's really excellent at the time, and it still is because it captures almost everything in exploration reports. There are 110 tables to capture all these reports. Being the old sort of database, it's very clunky because everything gets locked up into reports, and you need to link the reports. But nonetheless, that database has all the elements that you need to sort of determine what analytical type, what's the precision, what's the detection limit, etc. And I still strongly stand behind this. This database we started this in GSQ in 2003. It's grown from 0 to about 6 million data points now. And it's been upgraded multiple times by TerraSearch. And in the last 10 years or so, Map2Mine has taken over that upgrading. And it's still an excellent database, which I sort of, challenge you to sort of, use them if you can. The big difference here is this: we have transformed the data. It used to be in AGD 66, and now we have transformed it to GDA 2020. In terms of elements captured, these are the group of elements. Like I said, majority of them are metallic elements. The yellows are the ones that's outside the metallic, and they are very minor, 0.6% of it as well. So if you look at critical elements or critical metals, it's still in there, but you got to search for it, and you got to really attribute whether it's good enough for your use at all. Well, like I said, there's 6 million. It's a really heterogeneous database. It consists of surface samples, rock chips, whole rock, stream sediments and soil, and boreholes itself. This is a database, like I said, it's affected by those insights and analytical method. But the good thing is we captured all this data, and it's really important for users to review the data before you integrate it into your workflow. The 36 tables that captured all this data are shown here. But of these are the library. The LIB are the library tables that captures all the analytical methods, the detection limits, etc. Well, these are important when you start processing the data to make sure that it's suitable for critical metals. Another sort of strong point of this database is that it captured the detection limit. This is some work that I've done, many years ago, but it's still valid in the sense that in the blue are the range of backgrounds in common rocks. That's the sort of range. In yellow, the sort of darker yellow are the median sort of detection limit in the database, and the others, the yellows, are just the various detection limits itself. Well, that's for trace elements. Well, how do you use them? Basically, the usefulness depends on what stage of exploration. For example, if you're in exploration, you really need the high precision data on this end. The first thing you do is to check whether it's digested the right way. And the second thing is that if it's below detection limit or the background level, it's useful. If it's above, questionable. But if it's anomalous above, it's still useful because it's real. The other thing is that if you're into sort of blocking or sort of all proving, this side on your right hand side, it's valid because you are only interested in ore grade, and therefore you could sort of use them to integrate into your data itself. So basically, it has all the the bells and whistles that you need in exploration as well in mining as well. This is an example. The first figure here is just the stream sediments over the Mount Isa region. The second ones are, a single elements. In this case, it's the soil. Using single elements, you could still identify anomaly, or you could combine multiple elements into what we call a mineral or chemical indices to identify anomalies. So, therefore, for the usage, you could either look at one element for anomalies, or you could use a filter to sort of determine anomaly. Next group of things that we look at is the catchment chemistry. This is a work initiated by Geoscience Australia. Here we show Patrice Carritet and Glennis, one of our staff here, where we collaborated in, sort of sampling the catchment, not just, in the northwest area, but throughout Queensland itself. What it does is that this database is excellent for regional prospectivity, and I have turned this database into a prospectivity atlas for the whole of Queensland. Again, this is affected by size and digestion method. However, when you talk about targeting tools, that doesn't matter because it's all based on statistics. You still find where is most prospective and where is least prospective itself. These are the various reports, and there are more of these reports that has been released on the catchment itself that you can, just download, from the website itself. This is an example of, the output. Here you had gallium. It covers the entire Queensland. It pinpoints area where there's highest possibility of finding gallium versus the others. And it also covers 69 other elements. The second graph is for tungsten, where it covers, you see that there's a big concentration in the Cape York area, and that's for copper. As expected, you find copper in the Mount Isa region. Well, this is really cost. It covers, one catchment is about 5,000 square kilometers. So what we've done is we got a package of new funding to look at just the Cape York area. The Cape York, when I mentioned Cape York, it covers down to Georgetown area as well. This is the result from the National Geological Survey of Australia, or the NGSA sort of result. Very close, but it highlights that there is anomaly in that region for tungsten. When we refine it with our sampling, we zone in how it's a real anomalous region. And that's for tungsten, that's for bismuth, that's for gold. And like I said, you got 60 odd elements there that you could use to target. That fast track a lot of your exploration. Instead of going around doing stream sediments, we have done a lot of this for you already. So it's a question of just picking it up and go ahead, asking the right question, the how and the where it is. We also sort of combine all these elements into indices to come up with models that, that's applicable. And this is for the Cape York area because it's more refined. And this is the ones that are used for training this, sort of critical metal, understanding. And we had a good control of the sample itself. And the last part of the package that I talk about is a hydrogeochemistry. This is one, I think, method that's quite new. And I think, Queensland is one of the first states that tried or applied it in terms of mineral exploration. And I was really encouraged this, afternoon by talking to some of the explorers that they have used this, heavily in the exploration, and they do find success, or at least, sort of zone in based on what we found. And that's really encouraging for us. We have released 3 reports on this, 1 report on the eastern sort of Mount Isa, and 2 reports on copper isotope techniques. So what are we really sampling? We are not interested in surface water, but the formation water. Basically, when you pump a well, that drawdown cone in a well creates a negative pressure. And as a result of that, there's a preferential flow from the formation water up. And this is the water that we are interested in. But inevitably, you are getting mixed in nature from surface and the sort of formation water. And so it's important to really purge your well enough to get a good representation of the water itself. The water chemistry or the bore water sort of expression is good because you don't have to worry about this, granularity or digestion method. It's all in solution. But there is another complication, is that it's strongly dependent on the thermodynamics of the different elements. In other words, if you got, for example, Kennington, you get a lot of sulfur, you get a lot of lead, but you get very low lead in the water. The reason is that lead sulfate is insoluble, so it sort of drop out of water because of that. So it's this understanding that you have to sort of, look at it. And so lead is not a good element to look at. You look at what's next besides lead. Things like silver, probably, is a proxy to lead itself. So it requires quite a comprehensive understanding to target that sort of, elements. And that's why the report takes a long time, because there's a lot of to and fro's between GSQ and CSIRO to sort of get a right outcome for the report itself. The good thing about hydrogeochemistry is that it analyzed for 66 elements, and the data, after it's been curated, you could use it either as a single element to determine anomaly, or you could merge them together to find mineral indices. And there's some of the examples I showed you there, that you could combine them to find different kinds of systems to see if it exists or not. Where do I begin? Well, that's a song, I know, but in terms of hydrogeochemistry, well, the first step is to find that there is a bore. In Queensland, this is really we are really lucky, because the Queensland government insists or required all farmers or all property owners to register their bores, and basically every bore is registered, unless it's recently sort of drilled. So you have a sort of array of bore that you could work with, and also for each bore there is some crude metadata that you could use. And the important metadata we look for is the depth of the bore. String, sort of depth, it's generally not provided, but the depth itself is good enough that that's a deep bore. We could use that to look at the formation water itself. This is the results of the previous work that's done. In gray is the East Mount Isa things that we have compiled. The blue are the ones that we have worked with JCU. The purples are the boreholes that's been sampled by Moho with CSIRO, and the green are the ones that's done by Rio Tinto, but this is a confidential data itself. In last year, we sort of filled in a lot of this gap and extended it to the Georgetown area. This is the latest sort of coverage, all the way from Gregory down to McKinley. And we had a good coverage of undercover areas that will provide us additional sort of information of mineral potentially, targets in undercover areas, as well as around Georgetown area. We have expanded also the study, from just lead isotope to lead to copper, zinc, and strontium isotopes as well. And this, we had different collaborators, working on this. Well, from the earlier results that we did for Eastern Mount Isa, we identified 13 potential mineral interesting area. Using lead isotope, we found another 4, additional areas. And I think most of these are being looked into by explorers. And we applied copper isotope in one of the trials in the Jericho area, and it proved to be really successful in zoning in on the Jericho area. Now, for this new data set is still in the sort of preliminary stage of interpretations and processing. So I could only sort of put this out because the report is not out yet. So I shouldn't really be telling you the story, but I can't help it. Okay. This is a result for arsenic. You sort of pick up, there's some strong arsenic on the northwestern side of the Georgetown, and it coincides with gold too. I'm not saying anything, but there's an arsenic gold anomaly undercover thing. You look at zinc. That's 2 anomalies, one in the Boomera area and one in the Kamilaroi area. That's for zinc anomaly, and it coincides with copper too. And does that sound familiar? Well, that's the sort of the fact at this point, and we will sort of go through and try and sort of interpret it and integrate it with the other chemistry that we've done before. In terms of metal isotopes, we are looking at copper isotope. Basically, the heavy copper means that there is weathering of copper sulfides mineral. The good thing about this is we can train this data to look at mineral species itself. Like in this case, it's chalcopyrite, where we could zone in where chalcopyrite is potential. And this is for zinc isotopes, where it sort of picks areas that has zinc potential. Well, to sum it up, here's how the take-home message. Critical metal exploration. The future is you can't lump it together with all the other, sort of exploration and use a recipe book to go ahead. It's really important that you must focus on individual, commodity that you are after, or a combination of commodity. And for that commodity, look at the grain size distribution and the digestion method that's most suitable. If you need to do the multi-elements method to combine everything, you really need multiple analytical methods and multi-size fraction as well to cover the scope of the mineralization. And you could still use archival data and archival, sort of information in reports, but this has to be appraised before you sort of integrate it. And the take-on is groundwater and isotopic chemistry has great potential. It can, and this could be a game changer for exploration undercover. So to sum it up, this is a teaser again for you to think about. This is over the years of work that we've done. Is that these are the endowed elements in Mount Isa, and these are the endowed elements for the Cape York area. Look at these elements and try and figure out what grain size for these different elements, what's these sort of analytical methods for these different elements, and figure out how many size fractions and how many analytical methods are required if you want to sort of capture all the chemistry in Cape York or all this chemistry in the Mount Isa region. With that, I'll leave this puzzle with to you, and thank you.
Do we have questions, Joe?
Yep.
You're up. Thanks very much, Joe.
Thank you.
The next question. The next presentation will be from Matthew Greenwood, Manager of Regional Compilations at GSQ. Now, although the title of Matt's talk is a little more concise than Joe's, I'm sure you'll find it to be equally relevant and interesting. Matt will be giving a talk on GSQ's Geophysics program. Welcome, Matt.
Thanks, Evan. Following Joe is always super fun. Well done, Joe, on a great presentation again. I'll be talking about a range of recently acquired and underway pretty competitive geophysical data sets. And the fun thing I get to do is announce a whole bunch of new data sets that have been released either yesterday or today. So most of this you won't have seen yet. That's exciting for me, at least. Hopefully exciting for you guys. First one I'm going to talk about is our Ainsley mag survey. So this is keeping on building on the open file potential field data in Queensland and growing that high resolution survey coverage. We started in Mount Isa with those 5 surveys through 2017 to 2020. And then now we're moving out to Georgetown. So similarly, 100 metre line spacing, 60 metre survey height, 117,000 line kilometres. This was flown by Excalibur. It's a mag-rad survey primarily. We did have wingtip mag gradient on the plane as well. So we'll get mag gradient and enhanced TMI data out of that as well. It had 3 crystal packs on the rads, so better signal to noise ratio on the radiometrics. And also had the iChorus gravimeter on board the plane as well. So that's going to give us long wavelength gravity features there. That's going to be very interesting to see how we can compare that with some of our gravity in the Mount Isa area. I'll talk about it a bit later on, but we're looking at how we can infill that ground gravity coverage that I know is an essential data set for exploration, but bringing that down with groundwork is very tricky, both in a cost and time exercise. So how we can supplement that with airborne technologies is going to be a focus of mine, particularly in the next couple of years. So at the moment, we have about 8 million line kilometres of airborne geophysical data open file in Queensland, including fixed wing data, helicopter data, drone data. Currently, we don't have any regional drone data. There's a lot of issues there around payload weights, stability and electrical noise in the platform, and then flying beyond visual line of sight. But something I'm looking forward to in the future. So the INZ Mag survey is under final processing still. There's still some follow-up calibrations, compensations that have been done to the data to ensure we get the best quality data available. But we're looking for a mid-September release for that data set. And once we do complete that survey and that's a bit washed out, the next step I'll be doing is looking at building a merge, like I did in Mount Isa, of all the high-resolution data in that area to build a larger merge of the magnetics and radiometric data for that area. So even though it's not live, that is the data as it currently stands. So it's quite a spectacular data. You do get to see a lot of those intrusions, both in the outcropping areas around Georgetown and the shallow cover in that area. And we're going to use that data alongside some other new geophysics I'll talk about today, some new chemistry, like Joe was talking about, some geochronology and some field work to update the solid geology mapping and interpretation in the Georgetown area based on all this new data we're going to have in that area over the next couple of years. So we have some geologists who'll be working on that over the next couple of years as well. Moving forward to airborne gravity gradiometry, and this is some data that was released yesterday. So following the release of the Kenobi airborne gravity gradiometry survey a couple of years ago, we've flown two new airborne gravity gradiometry surveys, one up in the Georgetown area, the Etheridge survey, and one down on the Adavale Basin, which is funded by Geoscience Australia through the Data-Driven Discoveries program in the Adavale Basin called the Blackall survey. So these were both flown at 1 kilometre line spacing, about 100 metre terrain clearance, and looking at supplementing that data to infill the current ground gravity coverage for those areas. Both in these areas we had about 4 to 5 kilometre ground gravity, and so the 1 kilometre airborne gravity gradiometry gives us a much better data set to fill there, and the time frame and the cost to look at with AGG is much shorter in time and very comparable costs due to the extent of doing this on the ground. So it would have potentially taken us 2 years nearly to run this survey. So looking at the GDD or the vertical gravity gradient for both these surveys, I've got the Adavale on the left and the Etheridge or Georgetown survey on the right there. Moving forward to the GDED or the vertical gravity field. And I'll do a bit of a show and tell, haven't merged this into our ground gravity coverage yet, but that's going to be the next step. But currently you can see the locations sort of east of Tambo or west of Tambo or east of Croydon, these surveys. The current coverage of the ground gravity grid from the statewide or nationwide mergers, and then the new data coming into that. So I'll just look back again. You can see a lot more resolution, a lot more definition in those features, and they'll be used both to improve the solid geology mapping and also support some of GA's programs, particularly Adavale Basin, where they've conducted some new seismic surveys in that area as well. Houston talked a lot about AusAEM, so I won't talk too much about AusAEM, but just to say that is obviously a co-funded program between GSQ and GA. It's about this new program is about 27,000 line kilometres, covering 500,000 square kilometres. They're currently about 42% completed that survey as of the report I got today. They started down south in the block over the Adavale, and they're currently up flying around Longreach through to Rocky, that area at the moment. So they'll continue up the coast and continue those lines out there. The green lines there are obviously the pre-existing AusAEM 1, and the new phase of AusAEM is to extend those lines out to the coast. Following the AusAEM, we've also flown a high-resolution Excite survey or with NRG, a 2 kilometre line spacing infill on the AusAEM 1 area, north of Georgetown, in an area where we've got subcrop, a bit of outcrop, bit of subcrop, and some shallow covered areas there. Some very early preliminary inversions, thanks to USEN, who gave them to me yesterday or maybe the day before. So they're hot off the press. So I get to share these, and you get to share the Tempest ones that I hadn't seen as well. So that's a survey that is ongoing, and we'll have data released from that by the end of this year and available for explorers, and they will continue on with inversions and processing and some work on that data. Some work following on some older legacy AEM data. In 2016, we flew the East Isa VTEM survey, which was a an AEM survey around the Isa area and Cloncurry. Through processing that data, we realized there was lots of what we call airborne IP effects in that data. So Usain talked about the AEM survey, you charge the ground and then you get a response back. That response is not always purely a conductive response, but sometimes you're actually charging the ground at the same time and you're getting similar to an IP response where you're going to discharge at the same time. And that affects your voltages you get at the end. Makes it very hard to model the AEM data when you assume that the entire response is conductive, but there's a combination of conductive and chargeable response in that data. So this has been a project we've worked on with Imago, based out of Italy, who are modeling the airborne IP data and reducing that from the original AEM data, and then doing an inversion of the AEM data that gives us a much cleaner inversion for a lot of these lines where we do have significant airborne IP effects. The airborne IP effects are really mostly prevalent in the areas where you get very resistive basement rocks at the surface. Where you have conductive cover, you don't get a lot of that chargeability response, or it's not as significant in the result. But in areas where you do get quite thick resistive units, the airborne IP effects can be quite drastic, and so you get a much cleaner inversion set coming out of that data. So I'll flick through a couple of lines in that. We've released a report for this program, and probably tonight or when I go back to Brisbane, I'll be putting the data sets up on the open data portal as well for this. I would refer on your pages that A3 sheet with those QR codes that has the NEMI and the QIT and the reference collection QR codes. All the data that we're talking about today and tomorrow will end up on those landing pages. So if you're looking for any of this data, that's probably the first point of call. If you can't find anything, please let me know and I'll help you find that data as well. So we're looking at a line here from the Dugald, just south of Dugald River. And what we have here is the original CDI data from the initial, and I'm not going to call it inversion because you'll yell at me if I call CDI an inversion, but the models from the VTEM data. And then this is the resultant data from our follow-up inversion with the airborne IP responses removed. So you get far more geologically consistent inversion coming out of that data, and you can assess the misfit of that much better. If I skip down a bit further as well, and you do get your chargeability response, but you can also model up as well. It's important to know that it's not a pure IP response. We're charging it for microseconds. We're not charging it for a long period of time like you would in a standard IP survey. So it's very quickly charged and discharged. And that's just a comparison between the CDI and the inversion produced by Imago. Again, just another line with some interpretation of some of those features from the map brought down into the profile. Another new data set that we were able to release yesterday was our Carpentaria Conductivity Anomaly MT survey. So that was a magnetosphere survey, 248 sites collected by AGS. Hey, Trent. Over 2023 and 2024. It was a very large program, managed both by Janelle at the start and then Don Brown. And it was done in collaboration with Geoscience Australia, and there was funding provided through EFTF to enable that survey as well. The aims were really to produce a backbone of MT at a regional scale to enable a better understanding of what is a massive conductivity anomaly that comes all the way from the Cape York or the Gulf of Carpentaria and down through Queensland and in through Australia, into South Australia as well. So really, the last couple of programs we've done through MT, both in the Cloncurry MT surveys and the Boulia MT surveys and the profiles along CF2 and CF3 seismic, have really traced that anomaly. So this CCA survey was designed to really track down where that anomaly goes and get an understanding of what that feature is. As I said, this data was released yesterday, so that program of work and modelling hasn't been completed, but the data is available on the portal, and there's a preliminary tech report out there that describes the processing done to date and some very initial models produced of that survey. And also it adds to an extensive network. It's a bit hard to see on your screen there, but obviously we have our CCA MT survey there. We have all the Cloncurry MT and the Cloncurry Extension MT surveys up to the north. the Boulia MT survey down south, and then obviously along the majority of the deep seismic crustal profiles done in conjunction with GA, we also have MT. So we have quite a nice network of MT data across that, the Mount Isa Inlier and the Northwest Minerals Province as a whole at the moment. So again, as I said, the data release and the report was yesterday. There's a data set, the EDI files, the logistics and processing reports, a report produced internally by the GSQ on the work they've done to look at analysis of the data, as well as some Python code to help plot up that data MTPy and do your own modeling work as well. And there will be an inversion report and more inversion work done through 2024 as well. There's some very prelim mod-EM inversions along 2 sections through the survey. The first one here, the north-south line, CA0000, thanks for the naming, showing the Georgina and South Nicholson basins. And then the second line along east-west profile, CA20000, showing the Gidja structure, or the Gidja suture, sorry, and the CCA anomaly in the model. So again, very, very early inversions, but just really was processed up. And if you do have any questions about the inversions of the modeling, Janelle is definitely the best person who did all her PhD work on the MT data. So any questions on MT, you can go straight to Janelle, please. Something else we've done recently in the last couple of years, funded through the Queensland Resource Industry Development Plan, I'm going to get there in the end, is we had the CSIRO Mobile Petrophysics Lab, or MPL, housed the Exploration Data Centre down at EDC for the past year. This is looking at doing petrophysics along core samples, so as well as looking through the high logger or the mineralize or any other techniques, microanalytical stuff that Vlad and his team will talk about in a few days. We're also putting the reference core, some reference core, through the MPL and getting petrophysics on those core. So that's so it's a containerized system. So it comes in a container. It's got the Geotrek MPL system set up inside there, and we had an operator on it for the last year. It just went back to Perth last month. So the petrophysics we get from this, we're getting the core thickness, density, mag sus, radiometric gamma, conductivity, P-wave velocities, and XRF along those core. The data processing has just started, it's underway, and we'll integrate that with high logger, geochemistry, and other analytical work completed on this reference collection data. And a report and all the data will obviously be available to download from the Open Data Portal from GSQ, as well as the Open Scope Portal. Just something, the Staley data on the right here from Victoria, where they did continuous log across the entire core. We decided that what we do instead would be to focus on intervals along more core. So we've sampled, I think it was 500 trays of core over the year, looking at key intervals, both in the ore zones, in the alteration zones, and also in country rock, to enable petrophysics across the entire spectrum of the deposit to be input to geophysical modeling into the future as well. So all that data will be available, but it's not all the entire core, but it's sections along the core that represent key zones in that core. North Isa Seismic, a proposed survey that we'll be working up with GA over the next year to look at acquiring in 2025. So we'll start with stakeholder engagement for the rest of this year, looking at linking up the M1, M2 lines from the Century Mine area across through Gregory to link up with the CF1 line at Four Ways, and then running a line up past Normanton and then to Croydon to link over to the Georgetown Isa lines as well. So again, proposed line, so may change based on budgets and land access, but that is our proposed area. See, Trevor's drawing lines in his head already. Some other work in the seismic space where we have a postdoc, Al Chung, who's working at QUT and at the GSQ on ambient noise tomography using some legacy ANSEER data. So these were stations from about 2006 to 2011, using legacy noise to create an ambient noise tomography model, a velocity model across northwest Queensland. She's using a modified frequency time analysis, or FTAN approach, to modeling dispersion curves, and then building a series of 1D velocity profiles into a three-dimensional velocity profile. She will be presenting on this work at ASCG Discover in October down in Tasmania. Yes, I did say that right. And so she'll be presenting more on that there, but I have some preliminary results of the model she's been building. So that's a depth slices through the model, but also on the right there, we have the depth slice at 2 kilometers in relation to the gravity and the magnetics and our geological domains. So if you want to hear more about that, please do reach out to Al or come along to Discover and see her presentation there. Quickly, in conjunction with Geoscience Australia again, we went, Roger and Phil from Geoscience Australia went on a road trip to update the AFGN sites across Queensland. The AFGN sites, the Australian Fundamental Gravity Network, provides the datum for all gravity surveys to be tied into and to be leveled to a consistent datum. So this survey, this program visited 33 stations, 15 were in good condition, 18 had been destroyed in the time, 12 new stations were established to replace those destroyed sites and to add to the network. And they're all measured or reoccupied with Geoscience Australia's G810 absolute gravity emitter. So you have absolute gravity values for all those new stations available on the AFGN portal, which is at Geoscience Australia. And so here are the new sites, or the sites we've created as part of that survey there to update those new AFGN locations. Now, I know Mark did touch on the Digital Earth program. It's obviously a collaborative project between GSQ, SMI, and Euclidean. Building a 3D digital twin, and I just wanted to touch on Trevor's point that it started to be a digital twin of geoscience data, and it was very important. It wasn't a digital twin of like a common Earth model, but it was a visualization tool to understand the data, because you might have all your seismic and petrel, and it's really great to look at petrel, but you can't see the geochemistry relation, or you've got all your geochemistry and iogas, but you can't see your airborne geophysics. So the whole point of this was start to look at how we can visualize disparate data sets across an area and integrate with other things. But we looked at that and we thought, what else can we put in there? So we've already started to bring in ESG data, tenement data, and those things. But anything that's spatial, we can bring into this model. So whether it's forestry data or population data, we could bring anything else into this model as we go. It's really a data discovery tool. So it's not a tool we can bring data out of again, but it does link back to persistent identifiers of all the objects that you can see in it there. We're developing a standalone application which we're releasing in September, which, if any of the new nerds in the room, is going to be based on Unity. So it's going to be a Unity-based model for that. And while I'm talking, I'll just let that run. And I know you saw a quick video there, but I think I've got some different things to what Mark had there. We're looking through the Northwest Minerals Province 3D model created there, bring on the AusAEM lines as we come across. That's the inversion from the Cloncurry and Cloncurry Extension MT survey underneath Ernest Henry. And then as we zoom in, you can see the pit, the ore shell from Ernest Henry, and some of the sections through Ernest Henry sitting there. We're going to go into look at some core now in the Ernest Henry. So we're going to zoom in again further and look at some of the core imagery from the high-logger system. These are all located in space, so in correct space there. So sometimes it feels like flying through a bit of the Earth randomly. And then as we continue on, we're going to look at some X-ray tomography of that core. So we've gone from the entire country to micron scale size in the same model. All this processing is done in the cloud. You can run it on a desktop, you can run it on a laptop, you can run it on an iPad. If you're interested in this, tomorrow, if you come out to the core shed, I know we're looking at a lot of core from Ernest Henry. I'm going to have the deposit atlas. We bought the new deposit atlas from Ernest Henry into Digital Earth. So I'll have Digital Earth there as well. If you want to have a look and play there, definitely can show that there. But that's it. Thank you.